Hello everybody, this video is for Advanced Algebra 2. In this video we will be covering 5.5 applications of sine and cosine graphs. The learning objective for this video is that students will be able to apply their knowledge of sine and cosine graphs, amplitude, period, and frequency, phase shift, and average value to real-world scenarios. Our agenda for this video is we're going to work on 2 examples that involve tides, and then we're going to finish with a daylight example. And let's begin. Alright, so this word problem states water is 3 feet deep at low tide at 2 a.m. and 71 feet deep at high tide. The tide switches from between low and high every 6 hours. Graph and write a function to model this scenario. Alright, so I started by labeling my graph, as you can see on the screen, with height and time. If you need a moment to write this in, feel free to pause the video. Alright, so from this problem we know that our minimum value is 3, and this occurs at 2 a.m. So I'm going to put my first dot right here at 2 a.m. And I know that the high tide is 71 feet, and that switches every 6 hours. So from 2 to 8 is when our tide switches, so that would be our high tide. And then in another 6 hours, so that would put us at 14, which is off of our scale here. That would be low tide again. And I'm still going to graph this point because it will help us with our phase shift when we get to that point. Alright, so we know some key information here. I'm going to graph our midline, and then we can fill out our information about this problem. Okay, so that's our midline. We know that exactly in between 2 and 8 is 5, so we should have a dot on the midline at 5, and in between 8 and this would be 14 is 11, and so we should have a dot on the midline at 11 here as well. Okay? Alright, now I'm going to graph our first wave here, and I'm going to use a dashed line actually for this, and this is our... No, I'm sorry. I'm going to use a solid line for this because this is actually our situation. I'm going to use a dashed line for our initial one that we'll compare to. All right, here we go. All right, so that's our rough sketch of our graph here, and let's fill out the information that we know in this video. So, what's our average value? Well, exactly in between 3 and 71 is 37, so that's our average. Our range is between 3 and 71, that was stated in the problem. We know that the amplitude is the distance from the average to the peak or to the valley, and so we have a distance of 34 from the midline to the top or from the midline to the bottom. The period is 12 hours, which will allow us to find the frequency, which is what we'll put in our formula. And our frequency is 2 pi over the period, so 2 pi over 12. And if we need the official formula here, it's 2 pi over the period. And that gives us pi over 6 as our frequency. And so that's what we're going to have in our actual formula. And then we need to figure out our phase shift. Okay, so that's the tricky part in this graph, but here's how I would approach this problem. So normally, if we're looking at a cosine graph might start when x is 0, or when time is 0 in this case. A cosine graph might start at the bottom or at the peak, and so in this case the bottom is really close to this point, so I'm going to keep that one there. Okay. Now, I'm going to move all of these points backwards by 2, and we're going to see that this could have been related to a negative cosine graph because it's starting at the bottom instead of starting at the top. Okay, so that would be just our regular cosine graph. That could be our starting one, and we see that this graph is shifted over by 2 units to the right for all of these points. Okay, and so our phase shift, we could say, is 2 hours to the right. Okay. All right. So we have enough information now to write our function, and I'm going to continue my blue line just so that it keeps going all the way back to 0, but it keeps going like that, and this wasn't quite accurate over here. That should be the minimum value, so the graph actually keeps going up like this over here. Okay, and now we have enough information to write our function. Okay, so our function that we're going to use is cosine, because we're considering this as our starting point here, and that's at the bottom of the graph. And for cosine, that starts at either the bottom or the top. We're going to use negative cosine to represent the bottom of the graph here. And our function here should be that y is equal to negative 34, because we're starting at the bottom for our graph, cosine. We've got our average value over here, 37. We've got our phase shift of 2, which is right here, and we've got our frequency of pi over 6, which is right here. Okay, so we've got our 4 important values, and this indicates that our graph got moved over to the right 2 units from our normal cosine graph, and it's got all the other pieces that we need here. Okay. Now, if we expand this, we would be able to write it in a slightly different way. And the slightly different way that we can write it is y equals negative 34 cosine of pi over 6x. So that's just foiling, that's just distributing out this piece, minus pi over 3. And that's just pi over 6 times 2 gives us pi over 3. And then we see our average value plus 37 at the end. So those are 2 clear ways that we could write this function. And there's other options if you want to consider different starting points, which we'll see in our next couple of examples. But this is a good option for this graph because this point is really close to over here. Okay. All right. Now, a little bit of an application problem here. At what time does the tide first reach 50 feet? So what I would like us to do is just make an estimate of where this occurs on the graph. And so 50 is somewhere in between 37 and 71. It's like roughly in the middle. So I'm going to guess that our value that we're going to find here is like somewhere around this green dot. That's about when the height is 50 feet. And that will be the first time on our graph that it reaches 50 feet. Okay? All right, so here's what I would suggest to solve this problem. So we're going to write an equation to start. And you'll notice that our equation is exactly the same as the one we came up with, except for that we're solving for 50, and that's a y value. So I'm going to rewrite my equation as 50 equals negative 34 cosine of pi over 6x minus pi over 3 plus 37. So that's my same exact function, but I'm going to change y to be 50 because we're looking for a height of 50. Now we need to take some specific steps to solve this, and the steps are as follows. So we're going to start by subtracting 37 on both sides. And when we subtract 37, that's an easy step. We're going to get 13 equals negative 34 cosine of pi over 6x minus pi over 3. Now, we're just trying to isolate the cosine part, so now we're going to divide both sides by negative 34. So divide both sides by negative 34. And we're going to get negative 13 over 34 equals cosine of pi over 6x minus pi over 3. All right, so now we need to use our knowledge of inverse trigonometry for this. So we're trying to solve for a variable that's in the parentheses here. So let's rewrite this as inverse trigonometry. And because our values are in radians, we should be in radian mode. And so we're going to rewrite this as inverse cosine of negative 13 over 34. So that's just flipping these two pieces to write inverse cosine. And that's going to equal what's in the parentheses, pi over 6x minus pi over 3. Okay? Now, I'd like you to plug in this value on your calculator. And when you plug in this value, and let's double check this, but I'm going to do inverse cosine. Make sure you're in radian mode. Okay, inverse cosine of negative 13 over 34. And I get a value of approximately 1.96. Okay? So over here, we get 1.96 equals what we have on the right here, which is pi over 6x minus pi over 3. Okay, so now this is a little bit weird, but we just need to solve for x. So I'm going to add pi over 3 to 1.96, and you can do that on your calculator. You can change pi over 3 into a decimal. It's close to 1, so we're going to approximately add 1 to this, a little bit more than 1. And what we're going to get is 3.01 equals pi over 6x. Then we divide this. We divide by pi over 6 on both sides, and divide by pi over 6. Make sure you're careful with your parentheses, and you should get an answer of 5.75 hours. And if we wanted to change this into an actual time, this would be 5:45. That's 3/4 of an hour. 5:45 a.m. in this problem is when the height would actually reach 50 feet. And now if we go back to our graph, it looks like a reasonable guess. We had a reasonable guess here, 5.75 hours for this problem. Okay. All right. Let's move on to our next application problem. All right. The graph shows that the depth of water at a boat dock varies with the tides. The depth is 5 feet at low tide, so we can see this minimum value here of 5, and 13 feet at high tide. On a certain day, low tide occurs at 4 a.m., so here's our 4 a.m. value, and high tide occurs at 10 a.m., that's right here. If y represents the depth of the water in feet, x hours after midnight, use a sine function of the form right here to model the water's depth. All right, so we know a lot of things from this problem right away. Okay, I'm going to draw in our midline, and our midline is labeled here. It's 9, and that's our average value. So we're going to write 9 as our average value. Now, we know from this problem, our amplitude is how far it goes up and down from that midline, and that's a distance of 4. So we've got our amplitude, we've got our average, and that's two of our important values in our formula. That's A and that's D. Okay? All right, now we also know the period. So from peak to peak here is a distance of 12 hours. So we know that our period for this problem is 12 hours, so similar to the last problem. And to change that into our frequency, we do 2 pi over 12, and we're going to end up with pi over 6. So that's what's going to be in our problem for our B value is pi over 6. Okay, now the phase shift is always a little bit tricky, and because this middle part was highlighted, we're going to use sine as our trig function for this, and I'd like us to consider this starting point here. So we're going to look at this point right here. Let me use a different color, and I want us to think about how far it's been shifted from 0 hours. Okay, so normally sine would start over here, but now our sine graph's starting here. And this is exactly in between 4 and 10, so I know this value is 7. Okay, and so I can tell that this is a sine graph that's been shifted to the right by 7 units. So our phase shift for this problem is 7 units right. 7 units right. Okay. All right, now I'm going to sketch just what the original graph might have looked like. And this is going to be a rough sketch. It should end at around 12 hours here, and then 6 here. So the original graph might have looked something like this, and it got shifted 7 units to the right. So just keep that in mind for this problem. Okay. All right, so now we have our 4 values. We've got 4 for amplitude, 9 for average. We've got our frequency. We've got our phase shift. It's 7 units to the right to match this up. Okay. When we put all that into our formula, we end up with 4 sine, so that's our amplitude, pi over 6, that's our frequency, x minus 7, that's our phase shift, and then plus 9 at the end. Okay, so that would be a perfectly acceptable way to write your answer. If you'd like to distribute it out, you can just multiply both these values by pi over 6, and we get y equals 4 sine of pi over 6x minus 7 pi over 6 plus 9 at the end. Okay, so that would be a great way, 2 great ways that you could write your equation for this problem. Okay. Now there are some other possible equations that could work, and if we wanted to use cosine instead of sine, then these would be 2 good options. So the reason why, and I know it said sine here, so that's why we picked sine for these answers. I just want to explain why it could also be cosine if we wanted a different type of formula. So let's say we're using cosine. Cosine normally starts at the peak here. Okay, so we would be considering this to this, so this whole wave right here as our cosine wave, and that's shifted over 10 hours here. So for this first equation, it's all the same information except for I switched to cosine. 4 cosine pi over 6, x minus 10. That's a horizontal shift of 10 now instead of 7. And then we still have the plus 9 at the end. Okay? All right, so that's a great way that you could write it using cosine. And then there's another way you could write it using negative cosine. And so I just want to show that one. So what if we wanted to consider this as our wave here to here? So this whole part right here. Well, this is only 4 units shifted, but it's negative cosine because it starts at the bottom. So we would have negative 4 cosine of pi over 6, x minus 4 plus 9. And we could distribute these out if we'd like, but I just wanted to show you 2 other possible equations. So this was a distance of 4 here. All right, that is our second example. All right, on to our third example for today. If you'd like to pause the video and set up your graph like mine, you can do so now. Okay. A region that is 30 degrees north of the equator averages a minimum of 10 hours of daylight in December. Hours of daylight are at a maximum of 14 hours in June. Let x represent the month of the year, with 1 for January. Use a sine function of the form y equals a sine bx minus c plus d to model the hours of daylight. Okay, so let's plot what we know about this problem, and then let's see if we can figure out our 4 important values here. Okay? All right, so it says our value at, we have a minimum of 10 hours of daylight in December. So I'm going to put a dot at 10 hours in December. Okay, and we're going to use a little bit of logic here. So if we go backwards through our months, we would go December, November, October, September, August, July, June, May, April, March, February, January. 0 would be back to December. So I just want us to kind of notice that. It's going to be helpful for our graph, but 0 is December in this problem, and 12 is also December. And hopefully that makes sense a little bit because our period is going to be 12 months for this. So we could have these 2 points here. Okay? All right, so those are our minimums of 10, and then we have a maximum of 14 in June, so that's our 6th month. So we have a maximum of 14 here. And then that lets us know a lot of info. So our midline here is right in the middle, so that's 12, so right in the middle of 10 and 14. Okay, and that means we're going to have, in March, an average value of 12, and in September, an average value of 12. And I'm going to go ahead and graph my cosine function now on here. Okay, so it looks something like that. Okay, and now we have pretty much all the info that we need for this problem. So the minimum's 10, the maximum's 14, so that gives me an average of 12. I can look at my graph here and see the amplitude is 2 because the distance from the middle to the maximum and to the minimum is both 2. So we're going to have a 2 and a 12 in our formula for A and D. Our period is 12 months for this. And so similar to the other problems, we're going to just divide 2 pi by 12 to find our frequency. So 2 pi divided by 12, and we're going to get pi over 6. So that's going to be our frequency in our problem. It's going to be our B value. And then let's consider our phase shift. Okay, so it says we want to use sine here, and sine normally starts at our middle value. And so when we consider our phase shift, we're looking at this point. This would be the beginning of our sine wave. And I notice that it's shifted over by 3 boxes. Okay, so if I was drawing my initial sine graph, it would look something more like this. And then we'd be back to the middle there. So this would be just my normal sine graph. And I notice that this blue line that I have is shifted over by 3 units from that. So my phase shift is 3 units right. Or in this case, it would be 3 months right. 3 units right. Okay? All right. So what does this mean for our equations? So a first equation that we could write is y equals 2 for our amplitude, sine of pi over 6, x minus 3 for our 3 units right, pi over 6 for our frequency, and then plus 12 for my average at the end. Okay, so that would be it on an equation using sine. And if we distribute it out, we would get 2 sine of pi over 6x minus pi over 2. So if we multiply pi over 6 times negative 3, we get minus pi over 2 for our expanded formula here. Okay. All right, so that would be our 2 best answers for this problem because, like I said, we were using sine. Some other possible equations, for example, would be we could use negative cosine, and this is actually a really convenient one because if we started at this value, that's already where negative cosine starts. It starts at the minimum, so we wouldn't need a phase shift for this equation. It would just be negative 2 cosine of pi over 6x plus 12. Or we could use regular cosine if we wanted to consider starting at this top point instead. And so we could now shift it. This would be shifted 6 units if we think about that one. So we could use regular cosine, and y equals 2 cosine of pi over 6 times x minus 6. It's shifted over by 6 units plus 12. All right, thank you for watching this video. Until next time.